Welcome everyone. Today we will have a look on iodometry titrations, which are a category of redox titrations and which involve iodine as a reagent. So first of all, let us know about what are redox titrations. So as we have already studied earlier, redox titrations are a class of titrations in which there are two reagents, one is reductant and one is oxidant. There are two reactions going on simultaneously, oxidation as well as reduction. This is the very important clause of redox titrations, that reduction and oxidation should go hand in hand or simultaneously. If one of the reaction gets stopped in between the reaction process, then the whole of the reaction will stop. There is none of the condition like that ki oxidation and reduction will be conducted or will go separately. If there is oxidation in a reaction, there will be definitely reduction in the reaction going on, because there is a reason behind it. Because when oxidation is going on, then the electron released from a particular reagent will be captured or gained by the other reagent, by the other second reagent, which will be acting as a oxidant, or the second reagent which will undergo reduction, that will capture the same number of electrons that is being eliminated from the first reagent, and that will go reduction. So there is a reason the electron transfer happens from one reagent to another reagent in a reaction, and that's why the same number of electron changes are seen in both the reagents. So these are the redox titrations which we have already studied in detail. Now today we will study a class of redox titrations that is known as iodometry titrations. Iodometry titrations are a class of redox titrations which involve iodine in their method or in their calculations. Iodometry and iodometry are two common types of titrations which fall in redox titration category, and they are really very important for analytical chemistry. These two types of titrations are based on oxidation reduction reaction and can be used to determine almost all type of redox species quantitatively. Titrations are based on a reaction between the analyte and the titrant. As we all know very well, analyte is a reagent which is unknown and which is to be determined by a certain type of analysis, and titrant is a compound or a reagent which is known, which is a standard solution, whose help is taken to determine the quantity of or quality of analyte in a reaction. So the quantity of analyte can be determined easily from the reaction stoichiometrically, and the volume and mass to react completely with the analyte. So the analyte can be determined very well by using stoichiometrically reaction. Stoichiometrically reaction, what do you mean by stoichiometrically reaction? Stoichiometrically reaction are the reactions which are well balanced and which shows the molecular moles, number of moles of a reagent while reacting in between them. So every reaction should be written in a stoichiometrically balanced form. So the quantity of the analyte can be determined very easily from the reaction stoichiometrically, and thus the volume and mass to react completely with the analyte will be determined very well. So as I told you earlier also just now, iodometry titrations are a class of titrations which are used in which iodine is used. Iodine is used as a reagent. Iodine can be used as a reagent as a whole directly as an iodine solution, and it can be used as any salt of iodine, like potassium iodide, potassium iodate. So that's the difference between iodometry and iodometry. In iodometry, we use iodine as a direct solution, direct standard solution to react with the analyte. But in iodometry, we use any of the salts or any of the compounds of iodine to react completely with the analyte. This is the difference. We will study the difference in detail in upcoming slides, in upcoming PPTs. So now iodine is widely used for redox titration due to its capability of reacting fast. It reacts very fast. It's a very good oxidizing agent, and it reacts very fast with many species. That's why its applicability also widens up. Reversibility of iodine-iodide reaction is also an advantage when using them in redox titration. And second advantage of using iodine as reagent or going for redox titration or going for iodometry or iodometry redox titration is that iodine or iodide are reversible with each other, and during the reaction they can reverse into iodide form and iodide form could reverse into iodine form as per the case may be or as per the chemical reaction may be. So it is also advantage when we are using iodine in redox reactions or redox titrations. Iodine is moderately weak oxidizing agent. It is reduced to form iodide anion and follows I2 to 2I reaction. When iodine is used as an oxidizing agent, then it is reduced as the reaction depicts you. It is being reduced. This is the aqueous solution of iodine aqueous solution. You can see here very well. In bracket AQ is written. That means it is aqueous solution of iodine. It reacts with 2 electrons from the medium and gets itself reduced to 2I and gets itself reduced to 2I, 2 ions of iodide. 2 ions of iodide, that too in aqueous form. So since you can see very well from this reaction, the iodine undergoes a reaction with 2 electrons or absorbs 2 electrons or get reacted with 2 electrons, it attaches 2 electrons in it, that's why it goes reduction. For itself it goes reduction, it gets reduces to, iodine get reduces to 2I minus iodide. Okay, that's why, and we have told earlier also कि the ions, जो भी species जो खुद का reduction करते हैं वो दूसरों का oxidation करते हैं, right? दूसरे reagent का oxidation करते हैं और जो खुद reduction कर रहे हैं अपना, they are called as oxidizing agent. जो दूसरों का oxidation कर रहे हैं they are called as oxidizing agent, और जो अपना oxidation करते हैं दूसरों का reduction करते हैं they are called as reducing agent. So यहाँ पे आप लोग reaction देख के you can very well understand that iodine is undergoing a reduction reaction, is undergoing a reduction process. That's why for the other of the reaction, other reagent which is being reacted with the iodine, iodine does a very good oxidation of that second reagent. जिससे iodine react कर रहा है उसका oxidation करेगा और अपना reduction करेगा. That's why iodine is a oxidizing agent, because it is oxidizing the other reagent, the second reactant of the redox reaction or the redox process. This redox reaction is completely reversible. So the iodide ion formed serve as weak reducing agent that will react with the oxidizing agent to produce iodine reversibly, and thus with a number of, it reacts with a number of oxidizing and reducing agent. This is the applicability of iodine or iodide ion. We can see that this reaction is a reversible reaction. Depending upon the reaction conditions, iodide can very well serve as a very good reducing agent. By eliminating 2 electrons from it, it can very well get converted into iodine at any time of the reaction. And iodine, by absorbing 2 electrons or by reacting with these 2 electrons, can convert into iodide ion at any time of the reaction depending upon the reaction condition. So that's why if this reaction is reversible in a redox process, then both of the species, iodine as well as iodide ion, both of the species can very well act as oxidizing agent and reducing agent. So they can, what does that mean? What does that show? It shows that they can very well react with a number of reducing and oxidizing agents available. Okay, so that is the advantage of iodine and its iodide ion or its iodine species. Okay, that's the advantage or applicability of iodine and iodide salt. It can be very well applied, it can be very well used for number of several oxidizing and reducing agent, because at a time it is behaving as a oxidation, as oxidizing agent, and at a second time if it is in iodide form, it is behaving as a reducing agent. In iodometric titration, the analyte is reducing agent which reacts with the iodine to produce iodide, as we can see very well on the reaction. We can see on the reaction, analyte reacts with the iodine and get reduced. In iodometric titration, now comes iodometric titration. In iodometric titration, the analyte and oxidizing agent reacts with the unmeasured excess of iodide generated from a salt to produce iodine. So, in iodometric titration, iodine does not react with the reagent or analyte directly, it reacts with the reagent indirectly. First of all, iodide ion is formed from the iodine solution which reacts with the analyte, as you can see very well in the reaction. This is the reaction. The iodine is stoichiometrically related to the amount of analyte originally present in the sample. This is the iodide ion which reacts with the analyte or the sample. This is our sample. So, in this reaction you can very well see that we are not using iodine as iodine solution. It is not in I2 form. It is in I minus form, that is iodide. You can use any of the salt of iodine which is very well capable of undergoing redox reaction, such as iodide ion, iodate ion. These ion now reacting with the analyte get converted into I2, iodine. They get converted into iodine, and iodine is liberated stoichiometrically in an equivalent amount which is originally equivalent amount to the sample which is originally present in the analyte. The iodine may thus be titrated to determine the analyte concentration in the sample. The universal titrant of analyte is always, most of the time, is thiosulfate. They react quantitatively as follows. This is the reaction of thiosulfate solution and iodine. Here 2I minus. Hence, the reaction involving iodine can be used for analysis of strong reducing agent when they are reacting with I2 in iodometry, or oxidizing agent when they are reacting with iodide or iodate in iodometric titration. When they are reacting with salts of iodine, not iodine solution, then there are several oxidizing agents which can be serve as analyte in iodometric titrations. Iodometric titration is a type of volumetric titration in which oxidizing agent is titrated with the iodide solution. Oxidizing agent means analyte. The analyte which is to be determined or stoichiometrically. The quantity of analyte which is to be determined is the oxidizing agent. This results in liberation of iodine, which is then subsequently titrated by adding a known amount of standardized thiosulfate solution. This process releases the iodine. It is a two-step process, and this process releases iodine, which is again titrated with the standard thiosulfate solution. The end point is reached when the blue color turns colorless because all the free iodine is consumed up. In the end point, iodometry में end point पे blue color appear होता था because of starch and iodine reaction, but in this category end point में blue color colorless में convert हो जाएगा because all the free iodine is consumed up and it has got reacted with the thiosulfate solution. Iodometry is the titration of iodine which is produced when an oxidizing agent or analyte is added to the excess iodide. Then iodine is usually titrated, the iodine means this is the liberated iodine. This is the liberated iodine. First reaction में analyte आप देख सकते हैं यहाँ पे reaction में, this is the reaction. Analyte is titrated to the iodide. This iodide ion has been procured from any of the salts of iodine. Now, this iodide ion, after reacting with the analyte is a good oxidizing agent, so it oxidizes this iodide ion, and this iodide ion gets converted into I2 or iodine. This liberated iodine, this is the first step of the reaction. It is a two-step process. Iodometry titration is a two-step process. Then in second step, this liberated iodine, this is the second step. This liberated iodine is titrated with the standard thiosulfate solution, which serve as a titrant, okay. Got it everyone. So we can study that. Then the iodine, which is usually liberated, is titrated with the standard thiosulfate solution, and when all the thiosulfate solution consumes this iodine gets reacted with the thiosulfate solution, all the iodine gets consumed up, so there is none of the iodine is left in the reaction flask or titration mixture to show the blue color with starch. That's why जब तक ये iodine medium में present रहती है तब तक आपका solution blue color का रहता है, because आपका reaction mixture में starch present है, आपके titration mixture में starch is there, so this is of blue color. But when all the iodine is consumed up, once all the iodine is consumed up and get titrated with the standard thiosulfate solution, it is consumed up, that's why all the blue color goes colorless, okay, because all the iodine is consumed up and starch alone doesn't gives blue color, it gives blue color only with presence of iodine. So another titration should be then carried out with the same mixture again is carried out with standard thiosulfate solution to determine the relieved amount of iodine, and this relieved amount of iodine is stoichiometrically equivalent to amount of concentration of analyte which is present in the sample. For this, the mixture is titrated with standard thiosulfate solution, and starch mucilage is added as an indicator to determine the end point of the reaction. That's our iodometric titration. Now we can study the principle also, or we can go through the principle once again. In this titration, the equivalent amount of liberated iodine, as I have told you, equivalent amount of liberated iodine. What do you understand by this statement? Equivalent amount of liberated iodine. This statement shows the amount of iodine which is liberated here in the reaction is just equivalent to the amount of analyte which is present in your sample. That's why we are using this term equivalent amount of liberated iodine again and again, and this is very important whenever you write your exam or whenever you study it. It's always use this particular term, equivalent amount of liberated iodine, okay. Never use liberated iodine. Equivalent amount of liberated iodine is titrated with a standard solution of sodium thiosulfate solution using starch mucilage as indicator are called iodometric titrations or iodometry. It is an indirect method of titration. Because analyte is not reacted with the standard solution of thiosulfate or titrant directly. It is not reacted with the standard solution of thiosulfate directly or the titrant directly. It is reacted with the titrant indirectly in the second step, okay. So that's why it is an indirect titration, indirect iodometric method or indirect titration. Iodometry on the other hand is a direct titration. You can very well see in this diagram, we can easily depict that this is the standard thiosulfate solution which is filled in the burette. First, iodine solution which is as an oxidant kept there. It is reacted with the analyte which is in reaction mixture. This is analyte. Then after reaction with analyte, this particular iodine which is filled in burette is converted into I2 iodine. Now starch is added in between the process. This is another thing which is to be monitored, which is to be taken care of. Starch or the starch mucilage which serve as an indicator should not be added in the starting of the titration. It is added in between the process. After this analyte has converted all the potassium iodide into iodine solution, starch mucilage which is an indicator This is the indicator. It is being added in the titration mixture or titration flask. Now this same mixture, since iodine solution is present here, all of the Ki is converted into iodine, potassium iodide. Potassium iodide has converted all into iodine solution. Iodine solution में आपने starch डाला, that's why which color will appear? Blue color. So all the solution will be converted into blue color solution. So this is the blue color solution which is formed in the titration flask or reaction flask. Now this iodine solution will start titrating with the standard. This is standard solution or titrant. Standard solution or titrant, which will now react with the iodine present in this solution. This both will react, and when the reaction commences or all the iodine gets react with the sodium thiosulfate solution or the titrant or the standard solution, standard titrant solution or standard known solution, whatever you can call it. So when all the iodine solution gets reacted with the titrant or the sodium thiosulfate solution, it gets consumed up. It gets consumed up or finish off. Now none of the quantity of iodine is left. Okay. So when none of the quantity of iodine is left, will the blue color of starch will persist? Will blue color of starch will persist in the solution? No, not at all. Not at all. All the blue color, which is because of iodine and starch reaction, iodine and starch complex, will now not persist, will not be shown anymore. Now all the blue color will be converted into colorless, because now all the iodine is being consumed up. In this solution, it's only starch which is present there. Iodine, जितनी भी iodine solution था, that has reacted with the titrant or sodium thiosulfate solution. Okay, तो consumed up हो चुका है, खत्म हो चुका है. That's why यहाँ पे सिर्फ starch बचा है, and सिर्फ starch will not give blue color in itself. That's why at the end point, all the solution will go colorless, and that is the commencement of endpoint and conclusion of your reaction or completion of your iodometric reaction, iodometric titration. This shows the completion of iodometric titration or iodometric reaction. Now analytical applications. Iodometric titrations are applied in oxidizing analytes, especially as I told you earlier. For example, ascorbic acid, glucose, other reducing agent, etc. And oxidizing analytes, bromide, iodate, H2O2, copper sulfate. Okay. Then iodometric titrations are applied in most of the reducing agents and reducing analytes. For example, cysteine, glutathione, etc. other reducing analytes. So these are the applications. As we have already studied, in iodometric all the analytes will be of oxidizing nature. Okay, because they are oxidizing, their oxidizing capacity is the gist or is the key of this reaction. If they will not have that oxidizing capacity, they will not be able to convert that iodide solution or iodate solution into the free iodine. If free iodine will not be generated, then who will react with the titrant in the next step? Who will react with the thiosulfate solution in the next step? That's why its oxidizing capacity of analyte is very, very important for this reaction to go on smoothly. So various good quality of good oxidizing, powerful oxidizing analytes will serve as a good reagent, good reactant for iodometric titrations. And for iodometric titration, reverse is the case. In iodometric titration, all the reducing agents will behave as a good reactant. All the reducing agent, why so? Because all the reducing agents will react. It is a direct reaction, it is a single step reaction, iodometry. They will react with the iodide ion, iodine solution, and it will convert very well all the iodine to iodide ion. If they will have powerful reducing capacity, then they will be able to convert all iodine into iodide, right? So a powerful reducing capacity will be required to convert all the iodine into iodide ion. So that's why for iodometry, the type of analytes which are required is powerful reducing agent, because they reduce free iodine solution into iodide, and at the end point all the iodine will be shown and will give excess iodine from the burette, will give blue color with the starch in the reaction mixture. That's why in iodometric titration the reaction completion or the end point is marked by the appearance of blue color, and in iodometry it is being marked by the disappearance of blue color. So that was all we studied about iodometric titrations and iodometric titrations. This is important category of titration, iodometric titration and iodometric titration, and they are very well applicable also to various fields, because I told you earlier also, since these are reversible reaction, iodide can be converted into iodine and iodine can be converted into iodide depending upon the type of reaction and the reaction conditions. Okay, so its applicability is also very high, and this is the difference. This is the detailed diagram showing the iodometric titrations. You can see very well. This is the detailed diagram which is shown very well. Iodometric titration, which depicts iodometric titration, and in endpoint you will get a colorless endpoint, and in iodometry it is a single step procedure. The starch is added in the initial also, in the starting of the reaction, and at the end point we get blue color. As you can very well see, we get a blue color of end point. These are the applications, analytical applications. Iodometrics are involved various kinds of oxidizing analytes, and iodometry is involved in various kinds of reducing analytes. So students, that's all for iodometric titrations and the various important differences between iodometry and iodometry. So altogether we studied various important class of redox titrations which involve iodine and iodide, or we can say that iodine and its various salt as reducing agent and oxidizing agent. So that's all about iodine titrations serving as redox reactions. Thank you students. Thank you everyone.